is one takes a spinal nerve, such as the sciatic, nice and long, and then lays the nerve on top of two electrodes, one down here to stimulate, and the other to record the activity. And this is what you get if you apply a maximum stimulus to this sciatic nerve, so that all of the axons in the nerve are excited. You see a profile that looks something like this. This is time, this is amplitude of response. And what you can see is you get several different peaks. This first peak, which is labeled the A peak, occurs very quickly. Very soon after you deliver the stimulus, you can record the activity. That represents the fastest conducting group of fibers in that sciatic nerve. There's another peak out here, which is a bit slower, and then finally one way out here, which is a lot slower than the rest of them. Now, if we go back to the A peak, you can see there are subdivisions of this A peak. The first peak, which is the fastest conducting of the A group, is given the representation of A alpha. These represent the fastest conducting neurons within your body. You should be able to tell me the characteristics of these based on the fact that they are fast conducting. One is they have a large diameter, and two is they're myelinated. And so these are the largest diameter myelinated fibers in your body. The next peak is the B peak, A beta peak. The betas are not quite as large in diameter as the alpha, but still very large and well myelinated. There's another group here which doesn't show up as a peak. It's the gammas. I'll speak about them later. This is entirely motor neurons. The final group of the A is the A deltas. These are the smallest of the A fibers, but again, they're still myelinated. This B peak represents smaller, much smaller diameter, loosely myelinated fibers. These are pre-ganglionic autonomics, and I'll never mention them again. Then way out here are these very slow conducting axons, which constitute unmyelinated fibers of small diameter. Now this is what the electrophysiologists saw. The sensory histologists were interested in looking at the characteristics of sensory neurons that were relaying sensory information. And so what they did is they went back in and measured their diameter, for instance, and they devised their own rating system, and their rating system begins with group 1. Group 1 correspond to these A alpha. They're the largest diameter, well-myelinated fibers in the sensory nerve. The group 2 corresponded to the A betas. Now, since these are sensory histologists, they don't care about these because these are all motor neurons. The gammas are motors, so they don't care about them, so there's no grouping for them. The group 3 are the A deltas, and finally the group 4 out here are the C fibers. Now the reason I'm giving you this is because I'm going to, a couple of reasons, I'm going to be referring to them as either as group 1 fibers or A alphas, depending on the situation, but you should know what either one means. Our next lecture, reflexes, will talk about group 1 fibers, group 1A, group 1B fibers. They're just these large A alpha, fastest conducting, largest diameter myelinated fibers. The other aspect of this is I will expect you to understand what types of sensations or functions are carried by these. You don't have to actually memorize them. There's a table in your notes. don't spend time memorizing that table because we're going to go over all this, and if you learn the material we're going over, you will know which fibers carry which sensations. Now you are aware of your environment because of specialized structures called sensory receptors. The job of sensory receptors is to take the energy of a stimulus and convert it into something that the central nervous system can understand. And that something is action potentials, of course. I probably could have said that better, or at least in a different way, by saying unaided by machinery, the only thing that you are aware of are those things for which you have sensory fiber, sensory receptor. For instance, we're being bombarded daily by a whole spectrum of electromagnetic radiation. You're not using radio or watching television, etc. You're completely unaware of it, except for this small segment here, for which you do have receptors, and that happens for your visible light. The receptors are, of course, the photoreceptors, but otherwise you're completely oblivious to this. Now this brings me to the side. Sensations like sight, smell, taste. These are creations of the brain. They are the brain's interpretation of sensory input. For instance, 450 nanometer electromagnetic radiation is exactly that, 450 nanometer electromagnetic radiation, unless it gets intercepted by a human photoreceptor and interpreted by a brain, and then it becomes blue light. A more common example is if a tree falls in the woods and there's nobody around to hear it, doesn't make a sound. Well, a tree falling in the woods certainly produces impressions and rarefactions that emanate out in all directions from the site where it fell. The thing is, those increases and decreases in pressure are just exactly that. However, if there is an auditory apparatus around hooked up to a brain, those increases and decreases in pressure become a sound. Sounds don't exist without the brain. Colors don't exist without the brain, because all of this is just an elaboration by the brain of sensory input. It's your brain's interpretation of the world. All right, now there are several ways in which one can classify receptors. They used to classify them where the stimulus originated. Interoreceptors, it was stimuli coming from within your body. Extero, outside of your body. Proprio is position, body, your body, etc. They are now classified as to the usual stimulus to which the receptor is the most sensitive. This is called the adequate stimulus. And if we look at groups of receptors based on the adequate stimulus, we see these groups. The first one and the most varied one are the mechanoreceptors. These are receptors that are susceptible to physical deformation of one sort or another. Of course, the touch receptors are a classic example of such mechanoreceptors. However, the hair cells of the vestibulocochlear system are also examples. The stereocilia, deformation of stereocilia produces a receptor potential in these, which leads to either the sense of hearing or location of head in space. There are chemoreceptors. These respond, of course, to chemicals. The most common are taste and smell, but you have several chemoreceptors. For instance, there are internal chemoreceptors that can measure pH, metabolic concentration, etc. Thermoreceptors respond to temperature and its changes. The photoreceptors to light. And finally, nociceptors down here. These are receptors which respond to noxious stimuli, damaging or near damaging stimuli. Now let's talk about some of the properties of these receptors. One of the properties is transduction. This is the process by which these structures, the receptors, change the energy of a stimulus, no matter what form it's in, to eventually action potentials, which can then be interpreted by the brain. Now, the interaction of the receptor with the energy of the stimulus energy, always produces a change in the receptor potential. Consequently, the interaction produces a receptor potential. Now, the receptor potentials themselves have several characteristics, and this is an example of a receptor potential, which demonstrates one of the characteristics, and that is that the amplitude of the receptor potential depends upon the intensity of the stimulus. This happens to be a photoreceptor. If you shine a weak flash of light on the photoreceptor, the response is quite small. As the intensity of the flash of light increases, the amplitude of the receptor potential increases. What is also shown here is that not all receptor potentials are depolarizations. And since I've told you that the purpose of the receptor and its function is to transmit action potentials to the brain, this is counterintuitive. Hyperpolarizations in the wrong direction. We'll see how the eye makes up for this later on. So receptor potentials are graded. They can be either depolarizations or hyperpolarizations, and as we will see, they are created by things such as simple as mechanical deformation, as mechanoreceptors, or complicated biochemistry, which we'll talk about later as an photoreceptor. Now, what is not shown here is that receptor potentials are decrementally conducted away from their site of origin. You know what decremental conduction is, right? The reduction in size of the response as opposed to an action potential, which is always the same amplitude. Under certain conditions, is always the same amplitude. Right? So this is a decrementally conducted response. Now, there is a specific form of a receptor potential called a generator potential. The generator potential is simply the receptor potential in a primary sensory act. And it gets its name historically when people were looking at these primary afferents. They saw that if you delivered a stimulus to them, you got depolarization. The more intense the stimulus, the larger the depolarization, and if the intensity was large enough, these things would generate an action potential, hence the name generator potential. But they're simply a form of, they are the receptor potential of the primary sensory ending. Now, another aspect of these receptors is that of adaptation. Adaptation is the decrease in response of a receptor to a sustained stimulus. Now, we can, in general, classify two types of receptors based on their response to a maintained stimulus. One type is shown here on the left. Here is our stimulus box up here. These are tonic or slowly adapting receptors. You can see that not only does the receptor potential, not only is the receptor potential maintained throughout the duration of the stimulus, but so is the action potentials produced by that receptor potential. Now, there's another very different type of receptor, which is called a phasic receptor, or a rapidly adapting receptor.